Okay, this is hour 2 for Physics 1A, and we're now going to look at some more moment of inertia calculations. This one that we're going to look at now is a hollow cylinder that's rotating about its axis of symmetry, which is to say an axis that goes up and down like this. So we have a hollow cylinder with a uniform mass density rho. Okay, rho is uniform. With length L, inner radius R1, outer radius R2. This might be a steel cylinder in a printing press. It could also be like the wheel of a, the wheel of a roller skate or something like that, or the wheel of a skateboard or something like that. It's basically just, a donut. It's just your standard, just a ring. It could be a tube of paper towels. It could be anything like that, right? So that's our object. And it's being rolled or spun about its center, okay? And then it's being drawn here because there's just no way I could even do something close to as good as this drawing. We're just going to annotate on the diagram itself, okay? So ignore this little pink thing, okay? You basically just have a donut, right? I'm going to draw on here just so you can kind of you have this donut. There's the donut right there, right? It goes all the way to the inside. And the inner radius is this R1, the outer radius is R2, okay? There's our object. And we, again, want to calculate moment of inertia for this object. Now, to talk about how we actually go about doing this, we need to evaluate this integral. And in order to evaluate the integral, we need to ask ourselves, what is dm? That's the first thing. And remember that part of that is going to be doing something with volume. So in order to do this, what we're going to do is we're going to break our object up into small volume elements, and those volume elements are going to be cylindrical shells. They're going to have radius r and thickness dr. I hope that looks at least somewhat similar. I'm going to go back up for just a second to what we did here, right? Last time we broke the object up into slices. The thickness of the slice was dx, right? In this case, our slice, instead of just being a little piece of the object, is an actual geometrical thing in itself. It's a shell, okay? So in this case, the object is, we're going to split it up into shells, okay? Or tubes, you might say. So dm is this thing here. It's this purple thing. It's that hollow little tube that we're going to cut out. Okay? It's a hollow cylinder. Has thickness dr. Radius r. Okay, and this is what we're calling our slice. We're slicing the object up. We're imagining that we could split up our donut into tiny little tubes. A hollow cylinder of thickness dr. Okay? And, yeah, so that's dm. Notice that every point on this slice that we're making here has the same distance to the axis. Can you guys see that? Probably should even write that down. Every point on the slice has the same distance to the axis. Can you guys all see that? That's really important. Now, the next thing to do is to say that dV is going to represent the volume of the slice, and this is something we're going to have to figure out ourselves. what the volume of the slice is going to be. why don't you guys think about it for a second? How would you state what the volume of this slice is? You can type in the chat if you think you know what it is. What would it be? And again, the slice is the pink thing, right? So that's your dV. It's the pink thing. It has mass dm and it has volume dV. Mass dm and volume dV. What would the volume of a single slice be in terms of the given variables? It's going to depend on L, dr, and r. R outer squared minus r inner squared. Yes, that's right, Delvino. That would do it. We need to do some area. You want to do like area outer minus area inner, right? That's basically what you're saying, Delvino, right? Not area. Yeah, volume. Sorry. Volume outer. Right? Volume. That's what you meant, right? Yeah. Okay. Shells. Cylindrical shells volume. That's right. So let's before we answer this one, let's talk about what the volume of the whole object is, right? The volume of my object is going to be, well, it's a cylindrical object, and the volume of a cylinder is basically, well, it's pi times the radius squared multiplied by the height, which in this case is L. But realistically, what that's going to be for us is going to be pi L times the outer radius, but then there's a hole, so we have to subtract the inner radius. That's the volume of the whole object, right? Pi r squared would be the area of the top. You multiply by the length, that gives you the volume. But then you subtract out the whole. Okay? So if you wanted to do the same thing for our slice, dv, then I think you would do something like this, right? You're going to do basically pi L, and you wanted to do r outer squared minus r inner squared, Delvino. That's right? So the outer radius of our shell is r plus dr minus the inner radius, which is r. Right? That should be dv, right? Now we're going to calculate this, and I'm going to show you another way to do it. Because different methods are good for different people. Let's expand this out. So we have pi times L. R plus dr is the outer radius, right? See, r is out to here, but then you need to add the little dr. So you're going to have an r squared plus a dr squared plus the cross term, which is going to be 2 times r dr, and then minus r squared. That's going to be equal to pi L. The two r squareds are going to cancel, right? This one and this one cancel. And then I'm going to say, relative to this term, that dr squared, whatever it is going to be much, much smaller than 2r dr. You said not dr squared. Did I make a mistake? Bea, did I make a mistake there? I'm sorry, I just went all over. Alright, copy. Alright, so what we're left with then, okay, what I was saying is dr squared is going to be significantly smaller than 2r dr. And I'll give you a numerical reason why this is the case. But that's going to allow us to basically set this to 0. And our answer is just going to be pi L times 2, so I'll put the 2 right here, times r dr. That's our dV. Doing this, like this part of this, I feel like you'd probably do stuff like this in Calc 2. I'm not sure. So that's dV, but there's also another way we could do this, right? Another way we could have done this is to say, well, my object, okay, if I was to unroll that little pink thing in there, that is to say, suppose that I cut a piece like this and then I unroll it, right? It's going to roll out like a paper towel would, right? And it's going to become, well, like a rectangular prism, right? It's going to be something like this. It's going to be a sheet, right? Like a single sheet of a paper towel. That sheet will have some thickness, right? And it'll have a length this way. Now, if we unrolled it, then this side is going to be L. This thickness right here is going to be dr, right? And then this side, maybe you guys can tell me, how long will that side be? 2 pi r is the circumference, so that's this, right? That's 2 pi r. And I think you can probably see that the volume of this object, which we call dv, would then be equal to length times width times height, right? So it's equal to the same thing. You get the same answer either way, right? You'd get 2 pi r times L times dr. It's exactly the same. I like this method better, personally, but it's all about, what you like to do. I also like this method, except there was this step here that I kind of have to explain a little bit. So let me give you some examples here to put this into perspective. Let's say that the radius of a given one of these guys, okay? Let's say that I tell you that the radius is equal, let's just do something simple like 2 meters. Okay? But then I tell you that the thickness, dr, that has to be a distance too, right? Let's say that I tell you the thickness dr is like 1 micrometer. Ooh, let's not use micro. That might be something you've never seen before. I don't want to do that. You probably have, but let's say it's 1 millimeter. That is to say, let's say that it's 0.001 meters. 1 millimeter. That's our dr, okay? Now, dr should technically not be a fixed distance. It should actually be like, an infinitesimal. But when you start to apply things in physics and stuff like that, it's actually okay to give a value to these things. So what would we get? On the left-hand side, we would get 0.001 dr meters squared. Okay. On the right-hand side, we would get 2 times 2 meters, and then times 0.001 meters. And what do these become? Well, this one is going to become 1 times 10 to the negative 6, okay? And this is going to become, well, basically 4 times 10 to the minus 3. Oops, 3. Right? And now, within our calculation, we added these things, right? So if you were to add these two numbers together, this would tell you what dr squared plus 2r dr is. And what you're going to get is basically this. You'll get 4 point... What is it going to be? 3 digits, right? 0, 0, 1. What were my units? Meters squared, basically. I think I did that right. I'm putting my calculator to check. So it's going to be... Am I being loose with significant figures? What is this here? Oh, you lose it with sig figs. Yeah, that's right. That's right. Exactly. Yeah, you get the point. That's the whole point, yeah. I think I have this right. Let's see. 1 times 10 to the negative 6. You guys, please tell me if I make a mistake. It's really easy to make mistakes doing this stuff. Plus 4e minus 3. I left something out of this, by the way. How could I lose that so fast? Where did it go? I was just using this pen. Fall on the ground. Oh, there it is. Sorry, I left something out of this. That's the leading 4.001, but it's times 10 to the negative 3. Let me fix that. There we go. So you can see that this is a very small correction, right? Yeah, 0.004001 exactly. It's a very small correction, which means that you can effectively just neglect this term completely. And that's what we did right here. Okay? Alright. So, we're still barely even started the problem. We've only figured one thing out. So again, our goal was to find moment of inertia, right? Do that. That's our moment of inertia calculation. And we've figured out what dv is. So the next thing we need to do then is to relate dm to that. So let's do that. So my relationship is that dm is equal to density times the volume. It's a uniformly dense object, so if I take density and I multiply by volume, I'm going to get mass. Density times volume equals mass. So, in this case, we know what dV is. We know that rho is constant too, right? So what I'm going to do is I'm going to leave rho as a variable as we do this, and we'll put it in at the end, just for the nature of keeping things a little bit simpler in terms of the derivation. All right, moment of inertia is given by r squared dm, the integral. In our case, that's going to end up becoming r squared times rho, but rho is constant, so we're going to pull it out here, times dv. And now we can plug in what dv is. So we're going to get I equals rho. That's density, okay? Integral. R squared. That doesn't change. dV. dV's right there, right? 2 pi L R dr. Pull all the things that are not constant out of all the things that are constant out, so we'll get 2 pi rho L integral r cubed now dr, and the r cubed is because there's an r here and an r squared right there. Now we can't really do this integral unless we have limits. Looking back, now here's what you're doing with the integral, right? The integral is a sum, right? The integral is actually a precisely quantified sum, right? And you're summing up the moment of inertia for every piece of these shells. Each shell has its own moment of inertia. You find the moment of inertia of one shell, plus the moment of inertia of the next shell, plus the moment of inertia of the next shell, and you eventually add all those up together, and you'll get the total moment of inertia. And that's what the integral does for you. So the smallest shell would have a radius r1, and the biggest shell would have a radius r2. Given that that's the case, what we're going to get out of our integral is 2 pi rho L, that's from that stuff, and then we're going to be evaluating, what is it, r to the 4th over 4 between the limits of r1 and r2. That's going to give us 2 pi rho L over 4. Okay, here, let's do one simplification. Sorry, the 2's cancel, right? So you end up getting pi rho L divided by 2, and then times r2 to the 4th power minus r1 to the 4th power. And we're almost done, but the last thing we need to do is to eliminate rho. We have to say what rho is equal to. What's the density? Before we do that, do you guys have any questions? From here on out, it's going to be very plug and chug. Like, we're just going to say what rho is, plug it in. We're done with all the math and the physics. Maybe not the math, but... You guys have any questions? Okay. So, I have a notification. Oh, it's a different class though. Okay. Yeah, let me know if you guys have questions. So we've got the volume, right? If we go back to look at the problem, it doesn't say anything about mass, does it? But I'm going to say the total mass is going to be m. Just making some room. So we're going to say the total mass of our object is going to be big M. And now we're going to say, okay, density is equal to mass over volume. Our volume is given right here. So it's going to be mass divided by pi L, and then R2 squared minus R1 squared. So then when I plug that into this equation, I'm going to get I equals pi. And now I put m over v in here now, right? So I put m divided by pi L r2 squared minus r1 squared times L over 2. So there's an L here, and I'll just put the 2 down here. So I basically just plugged in for rho, and that's multiplied by r2 to the 4th minus r1 to the 4th. I hope this is clear what I've done here. I basically took the definition for rho, and we just plugged it in right there. Now what I'm going to say is this is going to reduce so the pi l's cancel, right? I'm going to write this in a slightly different way. We're going to have m over 2 I'm going to split this into a difference of squares. And this is divided by from the volume. And then, you know, cancel. We're left with basically m over 2 times r2 squared plus r1 squared. That would be the moment of inertia of our donut. I don't know what you want to call it. It's basically a donut though, right? It's not really a donut. Let's not call it a donut. This is a hollow cylinder with inner radius r1 and outer radius r2. Do you guys have any questions? Just real quick, just to show you, go back to our thing over, nope, not that one. Yep. Where is it? There it is. Hollow cylinder, right there. 1/2 m r1 squared plus r2 squared. That's what we just proved, right? So that's another one of the ones off the list that we've done now. I'll go back to the derivation here, maybe zoom out a little bit so we can see all of it. Do you guys follow that? This is really tricky. I don't pretend to believe that this should be easy for you to understand, but now that it's on, now that it's been recorded, and you can look at it on YouTube, I hope maybe it's something that will be useful to you guys at some point. Definitely really tricky. There's a lot of tiny details that you have to pay attention to, but I hope you guys were able to. Are you going to edit it on the homework? Edit it. Wait, did you mean edit? The importance of understanding the derivation is so that you can then apply it to another system. Yep, I'm pretty sure. I have to pull it up, but I'm pretty sure I have one for you guys that's like a triangle or something like that. Yeah. We'll see. And I think it's one of those, like, prove that kind of things. It's just a proof. So you'll know what the answer is, I think, or something like that, and you have to prove it. Now, these problems can change just a little bit if the density is also a function of radius, for example. Non-uniform objects. But they don't change considerably. You'd have a function for your density in that case. Like, you could say, for example, suppose this object is thicker on the outside than it is on the inside. I don't want to confuse too much, though. Does anyone... I also think it's important to do derivations, like, personally, so I understand where things come from. And, yeah, that's more of a personal thing. I mean, I'm a physics teacher, so I care about where these equations come from, but, you know... Okay, so there you go. Do we get... Oh, God, I kind of want to go straight into the next one, but I feel like we need a break from just the pure math to do another problem. The problem is, like, we still don't have enough information. I haven't taught you enough. We still can't really do any problems yet. Can't do this one, at least. Maybe there's one we can do that I didn't set up yet. Maybe one of these examples we can do real quick. Like, we could do this example here. Oh, I hate the fact that it's in slug feet squared. That's just going to confuse you guys even more. Let's see if these other books have an example, a version of that we can do. I think that your book does too. Yeah, I don't need the book. I can just draw the problem. Let's just draw the problem. This is a simple problem. Okay. Let's do the following problem. Oh, we're not done. Shoot. I just realized something. We need to derive the other two. So this was for the hollow cylinder, right? So what if I wanted to figure out the moment of inertia for a solid cylinder? That is to say, one for which the inner radius, R1, that was the inner radius, was 0, right? For a solid cylinder, what you would do is you'd say, let R1 go to 0. If we let R1 go to 0, we're going to get just 1/2 mass times radius squared. That's for a solid cylinder. For a hollow tube, completely hollow, this would be a thin-walled hollow tube. For this one, what you would do is you would say, for the hollow one, I would let basically R1 equal R2. And then what I would get would just be mr squared. Oh, whoops. Mr squared. And those are the other two on the list. It is harder to spin a hollow tube than it is to spin a solid tube. Okay. So that's two more of the ones on that thing at the top. We don't need to do a new derivation, we can just... Alright. So let's use the stuff that we have, moment of inertia and kinetic energy, to solve an actual problem. Suppose that what I have is, I have a cylinder, okay? So I have a cylinder right here. And I tell you that my cylinder has a mass that we'll call M, and it has a radius that we'll call R. R. And then around this, we wrap string. Oops, string. Yeah, switch. Switch. Still haven't figured out what I've done to cause this problem. Okay, so around this object we wrap string. So there's string that's wrapped all around here. And then we say that the entire system is mounted so it can spin on an axis that goes this way. Not being able to change colors is really annoying. Whatever. This is going to be our axis. There's an axis that kind of goes through the object like this. It's mounted. Okay, so that's our axis of rotation. And then to our string that's been wrapped around here, we're going to say that there is a mass, and this thing is going to have a mass of little m, and it's going to start off a height that we're going to call h above the ground. This is the ground. Restarting the program. That actually would work just fine. It probably would work. I could do that, actually. Let's do it real quick. Good call. Simple solution. Get my colors back. So a height h above the ground, okay? And so the question is going to be, if little m is released from rest, I'm going to find its speed right before it hits the ground. Oh my god, I haven't been recording. I am recording. Okay, good. Never mind. So that's going to be part A. And then part B is going to be able to find the rotational... find the rotational speed of the spool at this time. Alright, so pretty much this is going to be the initial situation. After some time has passed, the mass will have moved down to here, and the string will have unwound. Okay, let's draw it as a second picture, because I don't... Yeah, we'll just take our picture here, we'll copy it, and then move the mass down a little bit. So... that way we can have two different situations, or ground. So here's the ground. The mass M is now going to be here. And the string is going to be on the ground. And at this time, this whole system is going to be rotating with a rotational speed that I'm going to call omega, and the mass is going to be moving downwards with the speed that we're going to call v. Alright? If the mass is released from rest, find its speed right before it hits the ground. One other thing, I'm going to say that this is going to be a solid cylinder. The pulley that this is on is going to be a solid cylinder. Okay? Mass M, radius R. Alright? Release from rest, find its speed right before it hits the ground. So we're going to use energy for this. We're going to be using our work done by non-conservative forces is going to be equal to the change in kinetic energy of the system plus the change in potential energy due to gravity in this case. And we're going to assume that the spool, as it rolls out, we're going to assume that the string never slips off the spool. So, you know, for every rotation that this thing undergoes, the mass will move down a distance 2 pi r. Does that make sense? Each rotation that this object undergoes, you have to pull off that much string. There's no slipping that's going to occur. There's not going to be any friction, okay? But one thing we are changing is we're talking about the pulley now, right? That's the one thing that's different about this problem versus problems we've done in the past. We're looking at the effect that the pulley has on the motion of the mass, okay? Does that make sense to you guys? We're looking at the effect of the motion of the pulley on no way. Okay. Sorry, something distracting. Alright, so we're looking at the effect of the pulley. Now, to use this equation, we need to include the... First of all, we're going to say work done by non-conservative forces is 0. To use this equation, right, we need to include information about both of these objects here, okay? And, I don't know what all that stuff is there. Just undo. Just get rid of that stuff, okay? So, we need to write the following information down. We need to know what y initial is, we need to know what v initial is, and we need to know that's it, right? Over here, we're going to need to know what is y final and what is v final. Now, I'm already telling you that we're going to define this velocity as v, okay? And then y final, well, this just depends on what I define my axes at, right? So let's define this point to be y equal to 0, which means y initial is h, v initial is 0, and then y final would be 0. Did I do that too fast? Now there's something else we have to include in this, because kinetic energy is also going to include angular speed. And so I'm going to say the initial angular speed of my pulley is going to be 0, and the final angular speed of the pulley is going to be what I labeled up there as omega. And now let's write out our expression for kinetic energy. Kinetic energy now is going to be 1/2 the mass of the little object m multiplied by its linear final velocity squared minus initial velocity squared. That's the change in kinetic energy for the little mass, right? For the rotating cylinder, it's rotating only on an axis, and that axis is not moving, which means that its rotational kinetic energy is just going to be given by the moment of inertia of the cylinder times omega final squared minus omega initial squared, okay? This is really important for you guys to understand and remember that when you're doing energy problems from here on out, kinetic energy now means both of these things. It means both of these things, okay? The mass has translational kinetic energy, the one that's hanging, and the cylinder has rotational kinetic energy. You need to include both changes. And then plus the change of potential energy due to gravity, little mass, m times g times y final minus y initial, right? That's... Yeah, I can repeat that. When you have an object that's rotating, you need to include its rotational kinetic energy. If an object is rotating and translating, you have to include both. Let me give you an example of that. This is something we'll do tomorrow, but I just want to mention it. Suppose I have a wheel, like a cylinder, and it's just rolling along the road, okay? So it rolls from here, and then it rolls over to here, and maybe we draw a line to represent what's happened. It's rolling, and it's moving, right? This object could have some angular speed, but it might also have a velocity, okay? That velocity we often call the velocity of the center of mass. So a wheel rolling along the road would have kinetic energy that would be equal to 1/2 I omega squared for rotation plus 1/2 mv squared for translation. Both of them. You'd have to include both. Now, for the objects in our system, the cylinder is just mounted on some axis, so it just spins, right? It doesn't have this part. VCM doesn't change. It's just 0. Does that make sense? Specifically for the pulley, right? For the hanging mass, it's not moving. Sorry, it's not rotating, so you only have this term. Let me erase all these things down. Does that make sense to you guys? Alright, we're going to do problems like this tomorrow, or next time. Okay, so here is our energy conservation equation for the system. The change in kinetic energy for the small mass is right here. This is the change in kinetic energy for the small mass. Change in rotational kinetic energy for the pulley, and then the change in gravitational energy for little m. Also, the pulley isn't moving, right? But if it was, we'd have to include a term for its change in energy too. But it's staying still. It's mounted on an axis. Okay, let's plug in our zeros here. So what is 0? Omega naught is 0. Y final is 0. And V initial was 0. Let's plug in everything else now. So we're going to have 0. Whoops. Thought I switched. There we go. We're going to have 0 equals 1/2. Now let's put in the values. So VF we said was V. Plus 1/2. Okay, we know what I is. We just derived this. It's a solid cylinder, so I is m r squared. Keep in mind these m's are different. Plus m g, and then no. Yeah, we'll just do negative h. I don't like that. It's just going to be minus mgh. Let's just do it that way. So now, if I want to solve for v... Oh, I left something off, didn't I? I left omega off. There we go. There's an omega squared right there. Yep. Ah, there isn't. No, in this case there's not. Let me go back real quick, Kenny. Oh, no, oh yeah, you're right. The solid cylinder has a half in it. I'm sorry, my bad. Sorry. I'm going to put this in a different color so it's clear what I left out. It's 1/2. Because the moment of inertia of a solid cylinder is 1/2 mr squared. Thank you for catching that. I appreciate that, Kenny. So 1/2 right there. Alright. Now, one last thing here is that omega and V are not independent of one another. They depend on each other. Does anyone know how omega and V are going to be related in this case? That's right. The velocity v at which the object hits the ground should also be equal to r multiplied by the angular speed at which the object's rotating. This is true because of one of the things I said in the problem, which is that the rope doesn't slip as it unrolls. That means the speed of the rope going this way, right, is effectively the tangential velocity of a point on the disk, and the tangential velocity is related to the angular velocity via the radius right here. So that allows us to do this. Let's move the mgh to the left-hand side. So we'll have mgh equals 1/2 little mv squared, and then plus 1/4 mr squared. But what we can do is we can say omega is equal to v over r, right? And then just plug that into here for omega. That effectively eliminates one of our variables. Now we just have v. This step right here you will do in almost every rotational problem that you do. You should be ready to do this in all of these problems that you, as you're working on your homework. Not always, but very frequently you're going to be making this replacement. So now we have the ability to solve for v, because what we have now is what, 1/2 mv squared plus 1/4 big M v squared. Because if you see the r and the r here cancel, r squared and r squared. This is equal to mgh, as it says on the left. So now the velocity, I would say, is going to be equal to the square root of mgh divided by, there's going to be a 1/2 m plus a 1/4 big M. There's the velocity. It would just be a number. We need to know what the masses are. This equation tells us that the bigger the mass of the pulley, the smaller the velocity is going to be. And I think that should make some sense. If the pulley needs to gain energy, the bigger the pulley is, it's going to affect the velocity. Does that make sense to you guys? Yep, big M's the spool. That's right. Big M was the spool and little m was the, I guess it's not super clear. Yeah, but that's big M. Make it a little bigger. Alright. So that's the kind of calculation you can use moments of inertia rotational energy to do. It's, again, just the energy. Notice that I haven't told you guys any new physical things today, like new physical laws, for example. I've just described how we calculate something called moment of inertia. There's no new physics, except the idea of what moment of inertia is. Conceptually, it's just a new thing. It's like, how hard does something resist rotation? We're still going to be solving problems in the same methods we have in the past, like using energy and using torques and using forces and stuff like that. We'll still be doing that. Moment of inertia is just a new concept that we have to kind of integrate into our, or to put into our system. All right. Okay, so that's a decent problem. It's time for more theory. we can't get to some of these other problems until we get this theory out of the way. So let's do it. This day is a really heavy theory day. All right. So the next one that we're going to talk about, the next theory thing, is going to be the parallel axis theorem. The parallel axis theorem allows us to calculate the moment of inertia of an object about any point once we already know the moment of inertia about its center of mass. That's what this is going to allow us to do. All right? And this is how we're going to set it up. We're going to start with the coordinate system. No, really, we're going to start with an object. Here's my object. It's just some strange thing. Okay. This is the origin of my coordinate system. The, normal coordinates, like, this is going to be the x direction. This is going to be the y direction. Okay. Let's say that the center of mass of my object is somewhere... Well, I want to draw a line first. See that how, like, sometimes it does that, but then sometimes it gets all, like, smooth with the ridge, whatever. Let's say that my center... I'm going to make something really clear here. This is just some object. Alright. I'm going to draw a line out to some point right here, and I'm going to say this point is the center of mass of my object. Yeah, I'll just say CM. This point is the center of mass of my object. And the next thing we're going to do, I'm going to draw one more line. Just like there. Okay. I think I have all the lines that I need. I can start drawing distances on here now. Okay, so let's talk about the moment of inertia of this object that I've constructed here. This point is obviously the origin of my coordinate system. This point is the center of mass. Okay, and the way that we calculate moment of inertia, and I'm going to go back to our original definition, where moment of inertia was defined as the sum over mi ri squared. This requires that I break my object up into pieces. Like, let's say that this piece right here represents m sub I. Whoa. That is to say, this is a piece of my object, mi. This is going to represent that value for, yeah. And now what I'm going to do is I'm going to draw some distances on here for you guys. So I'm going to say, in this coordinate system, okay, about this point right here, that this is going to be the x-coordinate. Let's see if I can just drop a line. Can I drop a line from here straight down? Not quite. Nope, not like that. Each time I gotta click the shape thing on. Okay. Well, we're not gonna do that, I guess. So, we're gonna define this distance to be x. Let's use blue. We're going to define this distance to be x, out to where the object is. I'm going to define the coordinate of the object to be y, so this is going to be y. That is to say, it's just the y coordinate of my object, up to like about right there. X and y, those are the x and y coordinates of the mass, right? And really, I guess I have to properly label these. This is going to be x sub I, and this is going to be y sub I here. And then I need two more distances on here. I need to define a distance right here that's going to be, let's say, b. So I'm going to say that this is b, and then this is going to be a. And then I'm going to call this distance d. So d, a, b, x, I, y. I think I have everything we need. So now we're going to apply this. And we're going to say the moment of inertia of my object about the origin is going to be equal to the sum over mi ri squared. What I would argue is that r sub I is this length. I think that I should be able to do this. If I start from here, and I go to here, almost perfect, I guess, that is going to be r sub I. That distance right there, ooh, that looks awful the way I wrote that. This is going to be r sub I, that length. And based on the picture, you should be able to see that r sub I squared, according to the Pythagorean theorem, is going to be xi squared plus yi squared. So my equation for the moment of inertia about the origin is going to be the sum over mi times, times xi squared plus yi squared. This would give me the moment of inertia about the origin. Now, if I wanted to find the moment of inertia about, I don't want to call it center of mass right now, for reasons that you'll see in a second. Let's just say that I define the point right here to be P, okay? I'm just going to call that point P, and say that the moment of inertia about point P, all I have to do is to change my coordinates to be as if the origin was at point P. If the origin was at point P, the distance to mi, that is to say this distance here, and this distance here, I would argue, if you look at the picture, that this side is going to be yi minus b, and this side over here is going to be xi minus a. Can you guys see that? So then the moment of inertia about that point is going to be the sum over mi times, I would say, xi minus a squared plus yi minus b squared. Does that make sense to you guys? I want to stop for a second. Moment of inertia about the origin. You take your lines, you draw it out to where your mass is, you sum over mr squared, right? In this case, we said this was xi and yi, so r squared became x squared plus y squared. If I instead want to go about point P, the distances are smaller. You've got xi minus a here and yi minus b here. It's just different distances. Does that make sense to everybody? All right, let's put this all together. So now, the moment of inertia about point P should be equal to we have to square out these terms here. So we're going to get terms that look something like this. There's going to be a sum over mi. Maybe I do it one at a time. So the first expression here is going to break down to xi squared plus a squared minus 2x sub I a. And then that's going to be plus, the same thing for this one, yi squared plus b squared minus 2y sub I, and then b. Oh, whoa, I didn't realize I was drawing right there. Oops. And now we can expand this out. We'll get several terms. There's going to be terms that look like this. There's going to be sum over mi. I'm going to group some things. Xi squared plus yi squared and then plus there's going to be a term that's the sum over mi times a squared plus b squared. That's this one and this one. And then there's going to be two terms that are equal to negative 2a sum over mi xi, and then plus 2b, no, not plus, minus 2b sum over mi yi. Okay. I think I realized what I did wrong here. I was thinking at the beginning that I did this wrong. I'm pretty sure I made... Let me just think about this for just a second. I think the mistake that I made here was that I actually want this to be the center of mass for the object, the origin. So that what I had written down before is that this is actually also the moment of inertia of the center of mass. I'm sorry for that mistake. I don't have any notes with me. My notes are just the notes that I have here. I'm just doing this stuff off the top of my head. Yeah, sorry to confuse that. The center of mass has actually got to be this point right here for this derivation to be correct. All right, so that moment of inertia about the origin is actually the moment of inertia about the center of mass, and point P is about some point that's not the center of mass. That's actually pretty important. Sorry about that. Okay. Oh, and one other thing that didn't make clear as well is that the axis of rotation is basically coming out at you, so that the object can rotate like this, like in a circle around the what you call the z-axis, basically. You could say that the z-axis would be the rotation axis. All right, so we've got this big long mess, and what does it even mean? Well, a couple of these things can be simplified down. So first of all, this right here, the first term, is this. It's the sum over mi(xi) squared. So this is the moment of inertia of the center of mass of the object. The moment of inertia about the center of mass, I should say. The moment of inertia about the center of mass. Plus, a squared plus b squared is equal to d squared. Right? Because this is a right triangle. And a and b are just the distances. So this is going to be sum over mi. Well, sum over mi is just the sum over all the mass elements. So that's total mass, right? So the second term is basically m times d squared. What about these terms here? What is that one going to be? So, does that look familiar to you guys? Sum over mi(xi)? Does that look like something we've seen before? Yeah. Let me just zoom out just a little bit here so I can get some more space to work with. So, just as a reminder, we learned at some point that the x-coordinate of the center of mass of an object is equal to the sum over mi(xi) divided by the total mass of the object. So this term is pretty much equal to, you move the mass over, right? It's just basically m times xcm. Right? So let's just write that down then. So what we have left over here then is basically negative 2 times a, and then we just saw that that expression is basically equal to the mass of the object times the x-coordinate of the center of mass. And then the second one is going to be related to the y-coordinate, right, of the center of mass. But what in our picture is the x-coordinate of the center of mass equal to? If this is 0, right? So xcm is 0 and ycm is also 0. That means both of these terms are 0. That's 0, and that's 0. So what we've discovered now is that the moment of inertia about point P is equal to the moment of inertia about the center of mass of the object plus the mass times the distance squared, where the distance represents the perpendicular distance between the two axes, basically, right? And this is what we call, well, the parallel axis theorem. We can use it to do this problem. We're going to do the other problem first, but I think. So this states that the moment of inertia about some point P is equal to the moment of inertia about the center of mass, you need to know what this is, plus md squared. Okay? Let me give you a simple example of where we could do this. So we learned that for a long rod, awful, let's just use the shape tool. We learned that if I have a long rod, and if that rod has a mass that we call m, and it has a length that we call L, then the moment of inertia about the center of mass would be an axis that would go straight through the rod, and the moment of inertia about the center of mass of this object we derived to be equal to 1 over 12 m times the length squared, right? Oops. The mass times the length squared, right? That's what we derived, right? The parallel axis theorem says, suppose that I want to find the moment of inertia about some other point. Like, let's say I want to find the moment of inertia about this point, okay? About this axis, I should say. So this is going to be our P axis, okay? This is going to be the center of mass. To find the moment of inertia about this point, I simply need to know the distance d between these 2 points here. That's d. The axes are parallel. I hope you guys can see that, both coming out of the board. That's important. In this picture, d is equal to L over 2, though, right? So, the moment of inertia about point P, then, should be equal to the moment of inertia about the center of mass, that's 1/12 ml squared, plus md squared, so m multiplied, I'm changing my m's here. It's little m's what I'm trying to draw. Doesn't really matter that much ago. ml squared plus m times d, which is L over 2. And if you add this up, what you're going to end up getting is ml squared multiplied by 1/12 plus a quarter. And you're going to end up getting 1/3 ml squared, which is also something we derived earlier, right? That's just an example of how the parallel axis theorem can actually work. This also allows us to find the moment of inertia about some weird axis. Like, suppose that I want to find the moment of inertia about a point that is a distance of, let's say, like L over 10 away from the end. Like, if this distance is L over 10 right here, and then this distance is 4L over 10, I could find the moment of inertia about this axis if I want to. We call it Q. The moment of inertia about Q would then be the moment of inertia about the center of mass, which is 1/12 ml squared, plus the mass, and then times the distance, 4L over 10, and then we'd square it. Okay, does this make sense to you guys, what I'm doing? It's pretty easy to use, but I know that people get a little bit confused about this one. My god, what would this be? 16 over 100 plus a 12th? One over 12 plus 16 over 100. And common denominator here is going to be like 600, maybe 300. 12 goes into 300? I don't know. Whatever that is. So it's 25 over 300. It's 45, 48. You get some weird answers with some of these things. 73 over 100. No, sorry, 73 over 300. ml squared. Whatever. It's just a random point, but hopefully you guys understand the idea. Is that right? Let's see. 12 plus 16. So 16 over 100 is 0.16. Yep, 73 over 300. Okay, do you guys have any questions? If you know the moment of inertia about the center of mass, the parallel axis theorem can tell you the moment of inertia about any other axis parallel to the center of mass axis. Does that make sense to you guys? Let's do that for this problem. You have a disk with a mass m and a radius r, is welded to a rod with a mass 3m and a length 4r. We want to find the rotational inertia about point P, the free end of the rod. So, to do this, draw this a little bit bigger here. Let's like label what the pieces are. So the mass has, this is little m. The rod has mass 3m. And the length is 4r. So basically, if this is the radius r, then this is 4r. So r just goes from there to there. moment of inertia is a scalar. So the total moment of inertia of this object is going to be equal to the moment of inertia of the rod plus the moment of inertia of the disk. When you put things together, they just add their moments of inertia. The moment of inertia of the rod is just going to be 1/3 multiplied by the mass of the rod times its length squared. And the moment of inertia of the disk, well, we're going to have to use the parallel axis theorem now, because if this system is rotating about point P, it's rotating around like this, then the disk is no longer rotating about its center. And that requires that we use the moment of inertia of the disk about its center of mass. It doesn't look like what I want it to look like. The moment of inertia of the disk about its center of mass plus the mass of the disk multiplied by the distance. Okay, and what's the distance? The distance is going to be the distance d from the center of mass, which is right here for the disk. Not for the whole object, just for the disk. That's the center of mass of the disk. So this distance is 5r. That's going to be our d in our equation that we used before. Should be a little more clear about what equation we're using, right? So it's that equation. Go down here. We take, just for the disk, it's going to be the moment of inertia of the disk about its center of mass, plus the mass of the disk, right? That's the second piece, and then times the distance from the axis to the center of mass, which is 5r. All that added together is going to be our answer. Does that make sense to you guys? And does anyone have any questions? Okay, so what we're going to have then is going to be I equals 1/3. The mass of the rod is 3m. The length of the rod was 4r. The moment of inertia of the disk about its center of mass, if it's a solid cylinder, is going to be 1/2 the mass of the disk, which is little m, times its radius squared, plus 25 little m and then r squared. And we just gotta add all that stuff up. 3/3, 4 squared is 16 times little m r squared, plus, 1/2, plus this is going to be about 25.5. And then you end up getting, 31.5, right? That's right. Math. You'll notice. Okay, do you guys have any questions about that? I want you to notice one thing here, which is if you compare this, right, and look where it came from above. Can you see how little the fact that it's a disk matters? See, the two terms here, they added to 25.5, but the 25, which is the vast majority of this, of where the moment of inertia of the disk is coming from about this point, is just coming from the fact that the disk is some distance d, in this case 5r away. The fact that it's a disk doesn't really affect the answer very much, right? 41.5, 41... pretty much the same number, right? Roughly. Same ballpark, at least. So the fact that it's a disk doesn't really matter, actually. And if it's a bigger disk, it'd be a different story. But in this case, the fact that the disk is small relative to the distance, right? The radius of the disk is r and the distance is 5r. Made it so that the fact that it's a disk just doesn't matter that much. It's just that 1/2 compared to 25. 25 is way bigger than a half, right? So there you go. You're definitely going to have a lot of problems where you're going to make the assumption that objects like this can be just treated like points. Why do I say points? Well, one of the things I didn't bring up is one of the simplest possible systems that you're going to see show up on your homework. And that is, suppose I have a light string, I have a mass m, okay? And the mass m is, let's say, moving in a circle or something like that. The moment of inertia for this system, since there's just one mass, is just going to be m times the radius squared. This is for a point mass, where you just completely neglect the shape of the object. This is going to be one that's going to show up on your homework a lot. I didn't specifically mention it. It doesn't show up in the chart, but I want to mention it now because you'll definitely need to remember this. That if I have just a light string with a mass and it's going around in a circle, then this is the moment of inertia. Just that single m at a distance r away. You'll notice that this is the same as the moment of inertia of a hollow ring. Right? A thin-walled ring has a moment of inertia that's equal to its total mass times its radius squared. Ring. It's hard to read. And effectively, a ring has the same moment of inertia as a point mass, which I think is kind of interesting. And it's because all that mass is situated on the outer edge of the object. Yeah, when they're rotating, they're the same, exactly. These two things, in terms of their ability to rotate, are no different. It doesn't matter that all the mass is in one point versus all the mass being spread out like this. They're effectively the same. Once this thing rotates, it basically traces out a ring, right? So it is a ring when it's rotating, right? When you take the motion as a whole, at least. Okay, so that was, even after we had like about a 10-minute discussion, that's still been over an hour and 15 minutes, I think, that we've been talking, and we're reaching the end of class. So I think we'll just kind of wrap up here. I want to kind of give you a preview of what we're going to be doing next time. So there's so many things we can do with rotation, but there's a lot of build-up that's required. But one of the things that I think maybe you might want to think about that we'll look at tomorrow is, suppose that I take a solid cylinder, right? If you took physics at this school, I guarantee your professor showed you this. And then, right next to it, I put a hollow cylinder, okay? And I release them from rest at the top of a ramp. Which one would get to the bottom first? Would it be the hoop/ring or the disc? If I release them both from rest at the exact same location, which one of them would reach the bottom first? Anyone have any idea what the answer is? So one person says hoop, one person says same, and then you said solid. The hollow, because it has a higher moment of inertia. Okay, so that's something we're going to begin class with next time. You can try to do the calculation yourself. It's an energy calculation, and then we can investigate it, and I'll probably find a video of this or something like that. You can also just try this out at home, because a disc is like a coin, and a hoop is just anything that's hollow. So like a paper towel holder or a toilet paper holder, if you can find any of those, would be an example of a hoop. And you could put them on a surface, like a table, and you can lift the table up, and you can just see which one gets to the bottom first. I think the answer might surprise you. They can be any shape. The masses don't have to be the same. They can be different masses. It's the shape. It's only the shape that actually determines the moment of inertia, or at least determines which one's going to get to the bottom in this case. Okay. They can be different masses. They can be different sizes in terms of radius, but yeah. So you could do like a roll of quarters versus like a toilet paper tube or something like that. Okay, but that's going to be it for the recording. I'm going to stop the recording there.